Welcome to UVU CS3060 Lecture 6.7, where we discussed one more tool for synchronization called the Semaphore. So the Semaphore is a more sophisticated locking tool than we had with mutexes. They're kind of the next step beyond mutexes. In fact, you might consider what we've done with the integer variable in our examples. We've surrounded our integer variables so that we can increment it and decrement it without encountering a race condition. Well, what the semaphore is it is an integer variable. It is an integer variable that is protected by two atomic operations. One operation is called wait, the other is called signal. And really, what these two operations do, wait performs a decrement as long as the semaphore is not less than or equal to 0. If the semaphore is equal to 0 or less than 0, it will enter this busy wait, and it will decrement only if the semaphore goes above 0. When does the semaphore go above 0? When it's signaled. When you perform the signal operation on a semaphore, it bumps that up. You can use this wait and signal combination to provide locking on a particular critical section by using this particular semaphore. There are two types of semaphores, two ways to use semaphores. We'll start with this one first. The binary semaphore usually has an integer value of 0 or 1. If it's 0, the semaphore will lock when you wait for it. If it's 1, when you wait for it, you'll be allowed in, and it will set it to 0, allowing it to be locked for other processes. And then as you exit, as you signal it, it will increment that so that another can go in. And really, this just emulates a mutex. When you have a binary semaphore, that is just 0 or 1, you have something that is basically a mutex. The other way we can use this is we can actually use this as a counting semaphore. A counting semaphore allows us to use the integer variable inside the semaphore to range anywhere from the number 0 to as large as we want. This becomes very valuable whenever we have, say, a buffer, and we want to keep track of the elements that are in use or the elements that may be empty. And we don't want to allow a process to continue. Say, for example, if there are no empty elements, we want a thread that would add an element to that array to block until an empty element comes into existence. So we can solve lots of different synchronization problems with this. Here's another one. You can perform a situation where you have two processes, and you need to have a certain statement 1 that happens before statement 2. Well, you could have a semaphore that is used whenever statement 1 is executed. It calls sync, which causes process 2 to exit out of this wait and run the statement 2. That way you can preserve the order between statements. And of course, we can do this with counting semaphores as well as binary semaphores. So, how do we implement a semaphore? Well, here's the deal. We must guarantee that no two processes can execute the wait or signal on the same semaphore at the same time. So, semaphores implement locking inside the actual function. This means that the critical section problem actually gets moved into the wait and signal functions. So wait and signal become critical sections of themselves. So we could do this with using the busy waiting, which is where it loops forever and ever. And usually there's not a lot of busy waiting if it's rarely occupied. But if you're spending a lot of time in these critical sections, busy waiting is a waste. As you know, we're looping forever, waiting for one condition to change. and that takes up CPU time. A scheduler could give a CPU burst where all it does is spend time looping through that. And that's very much a waste of CPU time and not advantageous. So, if we want to do this without busy waiting, we can actually create wait queues. Remember that processes have states, and there's a waiting state. And in that waiting state, there are lots of different queues for I/O, queues for timers, etc. Well, we can actually create a new queue for semaphores. Each semaphore, we can have a waiting queue. And as we have multiple processes perform a wait operation on that semaphore, they can be added to a queue. And then whenever a signal is sent to a semaphore, that particular semaphore can be put back on the ready queue so that it can run, and then a pointer to the next semaphore would be made available so that that's the next one that would be unlocked. And what we would have, there's going to be two operations we have here. There's going to be a block operation. The block operation causes that particular job to get added to the queue. And a wake-up operation, which says wake up this particular process in the queue and put it in the ready queue. And we can see the implementation here. So now we don't have an infinite loop. We have a wait that takes a semaphore. That semaphore value is decremented. Now, if that decremented value goes below 0, it gets added to its list of processes and it blocks. It gets added to this wait queue so that it's not wasting CPU time. When a signal happens, this particular semaphore is incremented. Remember, all of this happens atomically. It checks to see if that value is less than or equal to 0. If it is, then there are processes that are on the list, on the queue, that need to be removed, and it takes the top process from that and performs a wake-up operation on that process to get it put back onto the ready queue. No infinite loops, no wasted CPU time. Using wait queues in the operating system allows us to make more efficient semaphores. Now, something we'll talk about in the next chapter extensively is called deadlocks. A deadlock is when you have two processes that are waiting forever for an event that can be caused by only one of the other processes. So let's use semaphores here, and we have both semaphores initialized to 1. Let's say we have process 0 that waits on semaphore S, and process 0 waits on S, process 1 waits on Q. So both of these are allowed to proceed because S is set to 1 and Q is set to 1. They're both set to 0 after these calls. Now we come to Q. Well, in this particular case, if S is executed and then Q is executed, that's fine, because then process 0 can come into its critical section, then eventually signal those particular semaphores. Same thing's true with process 1. If Q is waited on and then S is waited on one after the other, then this is fine. But if these two are waited on simultaneously and then the wait Q and wait S are waited on at the same time, both of these will block and neither one will proceed, and we call this a deadlock. Deadlock is where two processes cannot proceed because they're waiting on an event from the other. Process 1 is waiting for process 0 to signal S. Process 0 is waiting for process 1 to signal Q. This particular starvation, where we have indefinite blocking, it just is a problem since none of these processes will actually be removed from the queue. Now, there is a situation where we can have starvation where it's due to the something called priority inversion. This causes, so let's say, for example, we have two processes, a high priority process and a low priority process. Now, they both share the same resource, and they both will lock that resource as needed. If the low priority process locks that resource and the high priority process attempts and blocks, well, the low priority process will eventually unlock that resource and allow the high priority to continue. But what happens in a scheduler if you have a low priority process that has a lock, but it's not scheduled because there are a lot of medium priority jobs being processed? If the low priority process never gets time on the CPU, we have all these medium priority processes running and a high priority process that could block and not unlock. When you have a high priority process that cannot continue execution because medium priority processes are being scheduled, this is called priority inversion. Now, we can fix this by using what is called priority inheritance protocol. That's where if the low priority process performs a lock on something, it's still a low priority process. But if the high priority process comes along and performs a lock on the same resource, the operating system recognizes that that resource is locked by a lower priority process. So what happens is the lower priority process gets bumped up to the higher priority process priority. And we call this priority inheritance. That way, suddenly we have this low priority process that has all the priority levels of the higher priority level process and is able to run before medium level priorities. Thus, we don't have this priority inversion problem. So sometimes we have improper use of semaphore operations where we perform a signal first and then we perform the mutex. That's perform the wait. If you signal first, well, that's not going to help you with your wait later. Or if you wait twice, this will cause a deadlock. Or if you remove a wait or a signal or both. In any one of these cases, we can get deadlock or starvation. And we'll talk about that in Chapter 7. This brings us to the end of Lecture 6.7, where we talk about this Semaphore, a new tool for synchronization.